Hello and welcome to the presentation of our paper titled Encryption Proxies in a Confidential Computing Environment. My name is Ivan Godimenko and today I have an honor to present our results to you. The main results of our paper are that we managed to additionally secure the cloud encryption proxy of our partner Eperi against powerful adversaries by running it in Intel SGX trusted execution environment. We leverage the lift and shift approach of the SCOAN framework to transform Eperi into a confidential application. More on this in what follows. And we also evaluated the POC performance using benchmarks. Let's start from the main motivation of confidential computing. The need to leverage the benefits of cloud computing is enormously high currently. However, there are certain compliance and security restrictions which have to be taken into account. Outsourcing the operations of infrastructure with retaining the control over the applications in the cloud infrastructure, especially in the e-health domain, is very important. Moreover, separation of infrastructure and application operations is of paramount importance for certain applications in the e-health domain, for example. It means that we have to provide for the concept of securely separating the infrastructure operations from the operations of the application. Let's talk about what should be protected and why in this setting. Application data must be protected in the whole life cycle, within the whole life cycle of application processing in this case. And especially data in use, about which I will talk in the next slide, is of paramount importance. The code, mainly the code of the workloads of the applications, maybe also the code of machine learning models must be protected in the cloud. Sometimes and very often also against the cloud provider itself. And also the classical stuff such as secrets, tokens, passwords, master keys, etc. All of this must be protected, and in the cloud setting it is a challenge to provide for the adequate protection for all of these pieces of knowledge. Now let's talk about the 3 states of data which must be secured in the target setting. First is the data at rest, which is a classical thing to provide for. Often it is the protection of data at rest is realized by utilizing different forms of encryption. Data in transit is also a known notion where the data between different parties, applications, and especially cloud components have to be secured as being transferred from one component to another. It is often protected using their secure transfer connections, such as TLS, transport layer security, for example, or HTTPS if we are talking on HTTP protocol, and data in use, with the latter being a very interesting subject to look on, because the data in use reflects the data in processing by an application, or the data being operated upon in the RAM, for example. And this is quite a challenge to protect against, especially in case of cloud workloads, and especially in the case when these data pieces have to be protected against their cloud operator, or against the powerful adversaries which can, for example, dump the data from the RAM and analyze that in the future. The confidential computing provides for this, and before we delve further, let's discuss the trust assumptions in the confidential computing area. Usually the conventional trust assumption model can be seen as the top-down approach, where the application have to trust the underlying software, which has to in turn trust the operating system, further to trusting in VM layer, for example, if it's the case, and with the latter also having to trust the BIOS of firmware sets and also the hardware, of course. In a confidential computing setting, the trust is only required in a specific hardware, which is the trusted execution environment, and into the application itself, which is applying and using these notions to secure its workloads. As an example, TEE, Trusted Execution Environment hardware, we know Intel software got extensions, there is AMD SEV, Trust on hardware, and so on and so forth. Basically, the technologies which provide for TEE. And as you see here in the slide, the attack surface is drastically minimized as opposed to the conventional model, where you have to secure the whole stack in order to be able to provide for adequate security in this case. Therefore, the confidential computing, if realized in the correct fashion, provides for this for the security with the minimum attack surface. Consider the following picture, which considers the application and the hardware, Intel SGX hardware, as being a cryptographic processor providing for this confidential computing functionality, being the only trusted components in the whole stack. It means that in the trust model, only the application processing, for example, the confidential workloads, or for example, an encryption proxy, which is the case for our paper, and the specific dedicated hardware are trusted. The rest, meaning the operating system, virtual machine manager, and also the cloud tenant and cloud operator, are considered to be untrusted. In order to adopt the confidential computing into the real-world application, often different approaches are used. One of these approaches is partitioning applications into a confidential and non-confidential part, which often requires re-engineering. Native programming of SGX applications requires a lot of know-how and effort, basically to reprogram or repartition the existing applications or writing them anew. Therefore, the need for supporting unmodified source code implementations is high. For example, if there are applications which have been developed by the programmers who are unaware of confidential computing, these applications have to be put into a confidential computing environment. And in this paper, this is also our case, we used Scone, a special framework, to run Java native application in an enclave. And an enclave is a specifically secured area of memory, which is only accessible to the application itself. Let us look at our use case, which is cloud encryption proxy. A usual setting and a motivation behind the cloud encryption proxy, also the one from Eperi that we are using, is securing the workload of an enterprise against the cloud provider. In this case, for example, we are looking at Office 365, where the enterprises are actively working with this software using Teams, OneDrive, and Exchange, for example. But the trust model does not include the Microsoft or the service provider, and therefore the content of the messages exchanged over this platform must be secured. As a solution, a proxy is placed between the end user machines and the platform, and therefore the users, which acts as a transparent proxy, encryption proxy. As an example, the user can see basically everything in plain text, and for the end users it is transparent that a specific encryption proxy is placed between the end users and the cloud provider. And the cloud provider, in this case Microsoft, sees encrypted data only and maybe some tokenized data, meaning the changed data, which allows for specific search functions or clustering, for example. But important is that such a proxy is a security component which provides for privacy protection of the content exchanged between the users, and therefore this component in turn must also be protected. And therefore, if the trust model does not include the operators of this particular software, then we suggested to put the software, the gateway, into a confidential computing environment, and by this secure it against the operators, for example, who have admin access to the Eperi gateway in this case. Therefore, our motivation was to protect also the trusted encryption proxy against the cloud admins, and to provide for the so-called data in use protection. Recall I was telling you about data in use protection before, so that also the cases, the unlikely cases of memory dumps or other attacks against data in use can be prevented against in this case, due to the fact that this proxy can be run in a confidential computing environment. Let me show you the general flows of Eperi gateway without trusted execution environment. Basically, as I just explained, the application data is intercepted by the Eperi gateway, transparently encrypted or tokenized depending on the use case, and then sent to the software as a service provider, for example, Office 365. And then when the user would like to fetch the data, then the process goes backwards, and the Eperi gateway decrypts the workloads and then displays them in plain text for the end user, and the whole thing happens without any, the user is not involved into this, and it's transparent to the end user. Well, in our case, as I told you, the Eperi gateway itself was additionally secured and put into a TEE, trusted execution environment, with the help of a SCOAN framework. We executed the Eperi gateway in the SCOAN framework. As you see here, the architecture changes a bit in that the wrapped software is executed in a Intel SGX enclave by utilizing an additional step in the development pipeline, namely the so-called SCOANified derived name from the SCOAN, from the framework itself, where this gateway has to be additionally compiled, so to say, with the SCOAN software. Additional components have been added. This is the functionality of this wrapper or of this framework, and basically what we tested was how the application performs in their constrained computational computing environment. The details of it you can read in our paper, and I would like to provide you further insights on the experimental setup in our case. To test the setting, we had a web page behind the Eperi gateway proxy, which had to be fetched through the proxy, and we used the HTTP benchmarking tool, which produced experimental evaluation metrics, one of them being, for example, throughput load, and then how the latency is distributed. And we benchmarked it using the specific approach and specific benchmarking software. And the results of it I would like to present you in a second. We basically tested it with the Microsoft Outlook Exchange, which was configured under a custom domain in the backend. The intuition behind this was wanted to emulate the behavior of a normal end user setup, where a user is interacting with the Exchange, with the Microsoft Outlook Exchange, sending emails, and so on and so forth. The implementation was, we implemented these services as Docker containers on the Microsoft Azure platform on our tenant. And you see we use a VM 10 virtual CPUs with 32 GB main memory. So a relatively modest configuration. And the disk configuration in this case was irrelevant because all the services fit into memory. And this was also our main idea, to test how the operation, how the performance of the Eperi gateway looks like in a productive environment, in terms of how it performs under the workload. And here you can see some details. Against the details of this, you can look up in our paper, but as you can see there, we provided for some measurements here. One of them was the distribution of latency, and the other was the throughput distribution and the relation between the throughput and the CPU utilization. And one of the might be most interesting measurements would be the throughput and average latency relation. And maybe on this one I can present you that we have defined the regions which showed acceptable performance. In this case, for example, you see the throughput was measured into requests per second, and there was some cutoff factor after which the latency for the end user was simply not tolerable anymore. The idea is that we have shown in our with our deployment that basically it's technically possible to run Eperi gateway and such gateways, in this case Java-based encryption gateway, in a confidential computing environment. Their measurements demonstrate that there are some cutoff factors, so after which the approach doesn't scale well anymore, which means that when for productive environments, if Intel SGX is chosen, it should be carefully scaled, and their target infrastructure has to be scaled as well, because the performance of this also depends on the target machines, because the size of the size of the so-called enclave page cache, the size of the enclave, the size of the whole the performance of how much data fit into one SGX enclave heavily depends on the target infrastructure and on the size of the machine, which and the RAM size of the machine, and also especially also on the CPU type of the machine, because there are different families of Intel CPU supporting providing different performance. But I think that the most important statement here would be that we have demonstrated the viability of this. We have also provided and demonstrated the working areas where we can demonstrate the viable performance for the end user. And for productive environments, it has to be carefully challenged which particular target infrastructure configuration would suit to provide for acceptable performance and scalability. Well, again, to conclude the presentation, a powerful attacker model was addressed in our paper, such as root admin, and this model can be addressed and respectively provided against by using the TEE paradigm, by utilizing confidential computing based on Intel SGX. We could run and modify a Java application in a confidential computing environment. It is possible. We used Scone for this. There are also further other frameworks available. And as you could see before, we could successfully test the execution of our Eperi gateway in such an Intel SGX TE environment. There are also other technologies which provide for confidential computing paradigms, such as Intel TDX, AMD SEV SNMP, IRM Trust Zone. All of them have their one main idea in common, that there is some hardware anchor providing for the trust and also for remote attestation and measurement. I didn't have time to get today to talk about this, but you're welcome to ask questions on this, and please also read our paper for the details. SGX, so Intel SGX and AMD ECV are already available, for example, on public platforms such as Azure. And our plan was to extend our measurements and our deployments also to not only to Azure, but also to Intel TDX, to test it there. And also we wanted to check how other cloud platforms such as the GCP, Google Cloud Platform, which functions do they provide, and if this would be a viable option to try on. And on a further notice, I welcome you to test our to check out our video interviews and our video interviews depicting the topic in more detail with our team on YouTube. Here are the links. Please feel free to reach out if you need them or if you have any questions. We have provided some more contact on this topic. And thank you very much for your attention. And if you have any questions, I will be more than happy to answer them. Thank you very much for having me.